class. How did the coding go? Any comments, questions? I saw some people had sent theirs to me. There was one issue that a couple people emailed me about. Apparently, I left off one of the priors on there. Let me pull that up.
Hey, Perry, do you want us to send you our copies of that code?
Yeah, yeah. Or you can send me the posterior, well, send me the marginal posterior distribution with the true values. You just take like a screenshot of it and send it to me, make sure they converge. Of either the trace plots or the approximated marginal posterior densities. So what was the prior that I left off? It was on one of the betas, is that right? Inverse gamma, denorm. Denorm. Mu for beta 0. Did I leave one off? I think Mia and Meredith sent me something about that.
I didn't. I don't think you left one off. I think that there was no density function.
Yeah, that's what I emailed you about too.
Which one was that?
I think it's around line 355-ish, where you're doing the Metropolis Hastings.
Oh, right, yeah, for beta 0. That's right, I just did some, that's weird that actually worked and it didn't cause an issue. Yeah, some denorm, should be a denorm in there. So I can share my screen, show you what I'm talking about.
Yeah, that really confused me because it worked. Like,
yeah. It must have been that value, that sum of the beta was just so small right here, or they were so similar that it didn't affect it at all. So if these values are so similar to each other, then it's not going to have that big of effect on the Metropolis Hastings ratio. It'll just be 1 over 1 or x over x, whatever it is, and it'll cancel out. So that also is how, so now when we're thinking about this question about Bayesian inference, about the influence of the prior on the ultimate posterior distribution that we have, you can see there's two components in a model like this. There's the first component that has to do with the likelihood, like your actual data that you collect, and that's going to influence the Metropolis Hastings ratio in that first line. But then you add on the effect of the prior in this component here. So you can evaluate the effect of the prior on your approximated marginal posterior distribution by just getting rid of this part here and see if it changes your results. Okay. So that's one of the nice things about writing your own code here is we can manipulate things like that and see what the influence of the prior is on the posterior distribution. All right, any other questions about this script?
Yeah, Perry, this is maybe more general, and I know we touched on this a week or two ago briefly, but the order of how you code your different parameters. You mentioned that it shouldn't matter, but
right.
Can we talk for a minute about that?
Yeah. So we're going to be, when we do MC-MC iterations, we're going to be doing a large number of iterations. And ultimately, which one goes first is the only difference is going to be the starting values is going to influence the very first one more for that very first iteration. But we're going to end up throwing away all these, the very first iteration anyway as burn-in. So you could just think of this as like going around as in a circle, right? We're going to sample mu beta 0, then we're going to sample sigma 2 beta 0, then we sample all of these, then we sample beta 0 at the end. Then we loop around back to the top, then we sample this, and everything's just conditional on everything else. So it's like going in a circle. So no matter where you start in that circle and go around, or what the order of that is, it doesn't matter. So you can, if I want to, I could put this up here, and it's not going to change the results. I just move around my sampler for sigma 2 beta 0 with any place in here, and it'll be fine. Now, the one issue where you can run into trouble with this is when you have where you need very specific starting values, and if you don't have starting values that are right for the type of density you're using, then it can cause some computational errors. And here's one example. Let's say instead of, I'm going to just manipulate this a little to think of a different model. Let's say we have our data y comes from a binomial distribution with probability of success p, and then the number of trials n. And let me I'll write out the model here first, and then we'll go to the R script. So okay, so if we have, and I use this model a lot, where we have data y, there's some type of counts, and maybe they're counts of animals, and we know we missed some of the animals. We don't see them all. Some are hiding in bushes. So we assume that yi is binomial, and it has some probability of success p and some number of trials n. So interpreting these in a wildlife biology standpoint, n might be the true number of animals that are really there, and y are the ones we see, and p is the proportion of those we see. So p is like a detection probability, the probability we actually detect the animals that are there. N is interpreted as the true number of animals that are out there, but this isn't always known. So we're trying to estimate what n is. We don't always know what n is. So n is going to be a parameter, and we could say n comes from a Poisson distribution, and then there's some expected value of n, or some intensity lambda, and there might be covariates with lambda that equals beta 0 plus beta 1 xi. All right, so we have a model here, and then we have priors on beta. And are those the only priors we need? No, we need something for p. P is between 0 and 1, so we could say a beta distribution. All right, so we have our model here. Now, when we develop a Metropolis Hastings sampler for this, we're going to have to choose starting values for n, because n is unknown and it's a parameter we're going to estimate. But there's some conditions on n that we have to choose for starting values. And the main condition is n has to be greater than y, because if we try and put a value in n here that's less than y, then we're going to get an error when we try and fit this. So I'll show you where we get that error when I go to RStudio. Well, let me just use Emacs for now. So if I say I'm doing the likelihood portion of this, and I have my likelihood for the binomial distribution, and I have my data and my size and my detection probability p. Size is going to be our n. If I say y equals 5 and n equals 7 and p equals 0.5, you'll only be able to see, oh no, I can fix this, okay. There we go, all right. When I calculate the likelihood of these data, it'll give me a value that's negative 1.80. But if I choose starting values now for n to be 4, it says negative infinity. It's not possible, right? So it doesn't work. And what can happen when we're choosing the order of our sampler is if we try and sample n, let's see, if we try and sample n so that somehow it gets out of line with maybe lambda, and n, when we're sampling it, falls below our value of y, then it's going to have there's going to be computational issues. So those are kind of the circumstances when we have to be careful in which order we sample our data. And really, this is more about choosing correct starting values than the order in which we sample our data. But sometimes if we sample these in order, we might get errors like this. So if we're sampling values for n and we choose a value of n that's less than y, we're going to get a problem. Okay. But in principle, it doesn't matter which order you sample from, as long as you choose correct starting values. All right, any other questions about anything in general? Okay,
So,
I'll go ahead,
sorry.
James. Go ahead.
So for the lab, I noticed that like for some of the values of like beta 1 and stuff, they didn't fit on the true value as much as like others.
Yeah.
And is that something, does that come into like your interpretation of the data and stuff?
Yeah, that's a good point. There is this paper by, I think it was Little in 2006 that talked about the methods that we were doing, and they called it calibrated Bayes. So, and I think it was in the journal Statistical Science, which is kind of like bioscience. It's more the journal Bioscience. It's more, it's a peer-reviewed journal, but it's more popular science than other journals. So it's made to be readable and more general to a wider audience, less jargony type stuff. And in that paper, they talk about this idea of if you choose a true value for parameters and you simulate data from those parameters, then you think you should be able to simulate posterior distributions that cover, like the 95% confidence credible intervals cover that true value 95% of the time. And that's this idea of calibrated Bayes. And I think the journal's something like combining a roadmap to frequentist and Bayesian statistics. Not the journal, the article name is a roadmap to frequentist and Bayesian statistics. But the interesting thing is there is no theory in Bayesian statistics that says it has to, that the posterior distribution has to cover the true value. It seems like a good idea that it should, right? If you generate data from true parameter values, you would think that you would want those posterior distributions to cover the true values. And I think we could probably agree on that. But there is no theory that says it has to. And it's because it's this Bayesian inference is this combination of our likelihood and our prior information. So we could develop priors that would pull away that posterior distribution from the true value really easy if we had really informative priors. But when we do this, we want to use kind of vague priors to see if it actually does cover the value. So to get to your point, James, we would think, kind of borrowing from frequentist principles, that if we were to simulate 95 data sets, or 100 data sets, if we were to simulate 100 different data sets, and do this exercise that we did in lab or for homework 100 times, 100 different times, that about 95% of the 95% credible intervals should cover those true values. And when you see one that doesn't quite line up, it might be just because of the random draw that we observed with the data. So when we sample data randomly, there's some stochasticity to it, and sometimes it leads to data that, if you take the mean of the data, it's quite a bit different than the true mean that you use to simulate the data. So if we say our norm 100 samples and we set the mean at 5 and the standard deviation at 3, on average, the data are going to have a mean exactly equal to 5. But for any one data set, it may be something like 4.4 or 6.3. And then when you see those posterior distributions that are kind of moving a little bit away from the true value, it could be due to that stochasticity in the data. But if we made an infinite sample size, then we would expect that red line to get closer and closer, the true value in that red line to get closer and closer to the center of that posterior distribution.
Okay, thank you. Yeah.
Okay, I remembered my question, and it's kind of about how to think about the 5 beta terms and how year fits into those alongside season, because we all coded them as betas. And so just thinking about those posterior plots, we have like how to think about that beta term a little bit more.
Oh, right. We were going to talk about interpretation too today. So let me pull up the solutions to that script, and then I'll run it. All right. Did I write over my solutions or delete all my solutions? Oh, right, wrong script. All right. So let me execute this code here. We never formally covered auto tuning. Has everybody looked at that to see kind of what's going on? Any questions about that? While this is running, I'll just explain it. It'll take 1 minute. We choose tuning values to control the spread of the proposal distribution. Sometimes we want that acceptance rate of our proposal to be about 40%. So what I have here in the auto tune is as if I say the acceptance rate divided by the number of iterations is less than 30%, we're going to make the tuning parameter smaller. If the acceptance rate is greater than 50%, we're going to make the tuning parameter bigger. So that's all that is. It controls that tuning parameter for us, so we don't have to run it, change the tuning parameter, run it, change the tuning parameter. And we do that for each parameter. Often I'll I'll put a if, because these if statements can be pretty slow and slow down the code quite a bit. I'll put an if statement in front of all of this, and I'll just say on every 100 iteration, run through all of this. And then it only changes the tuning parameter every 100 iterations. So that will speed up it quite a bit.
Can I ask another quick question
Yeah.
while it's running?
Yeah.
One of the mistakes I made was every time I calculated mu dot beta 0, I would recalculate like beta 0 dot star.
Let's see.
Is that so? Like, yeah, so like for every single one of these mu dot beta 0 and sigma squared dot beta 0, I'd also recalculate like a beta 0 dot star. Like what we do with mu dot star. Is that only ever the kind of thing that you would do for mu?
Yeah, so what you're saying, what you did was you put this thing into.
No. I put
okay.
like beta 0 dot star
Beta
are
0.
like under there. Yeah, under that I put like beta 0 dot star and I recalculated it using sigma squared dot beta 0 dot star.
Oh, I see what you did. Yeah, that is, remember we want to only change one parameter at a time. And we're going to treat beta 0 dot star. Let's see, where's beta 0? Yeah, beta 0 dot star is fixed when we're looking at, oh, I'm at the wrong spot. Okay. So you changed this to beta 0 dot star here. Yeah, we're going to treat this as fixed when we're sampling the mean of that value.
Okay.
So we just change one parameter at a time, and even though mu dot beta 0 is closely related to beta 0, it's the mean of all the beta 0s, we're going to treat this as fixed, and we're going to vary this. Now, if it was deterministically linked to it, that is, if it had an equal sign instead of a tilde sign, then you would want to update it. And that's what we see when we have this right here, because mu dot star here is deterministically linked to this function of the beta. So then we have to update it, because if beta 0 stars, then mu changes. If beta 0 changes, then mu changes.
Okay. That makes sense. Thank you.
Yeah. When you have the equal sign, you need to add that extra. You need to change everything else that depends on it deterministically. Okay, so it looks like this finished running. You can look at the trace plots. So these are the betas, and how many betas do we have? This is laggy. Oops, what happened? I didn't want to run that. Oh, I see what I did. I executed the whole thing. Sometimes these readline functions here are sometimes nice, because if you're looking at a bunch of graphs, it'll stop the graph at each iteration in a for loop. So I can look at all my betas here by writing a for loop around it. But they're also really annoying if you forget about them, because they hold everything up until you hit enter a bunch of times, until you get all the way through the for loop. And you can't get out of it. So use read line with caution. All right, while this is lagging, I'm going to go to the whiteboard and we'll talk about the model again, because that'll be helpful for us in terms of interpretation. All right, so this model was different slope, different intercepts, so random slope, random intercept for each stream, right? And there was years. Kelly, can you remind me what the model was?
Yeah.
Why?
No problem. Yeah, it was Yij is log normally distributed with mu I comma sigma squared I, and I for every ith observation in group J. And then we had the 7 J sites. And then do you want the process model next?
Yeah.
Okay, so the process model was mu I equals beta 0J plus beta 1J times xij plus beta 2 times x2ij plus beta 3 times x3ij plus beta 4 times x4ij plus beta 5 times x5 plus beta 6 times x6, where the covariates are x2 equals fall, x3 equals winter, x4 equals spring, x5 equals year, x6 equals year squared, and I believe x1 equals stream flow.
That's right. Yeah. Okay. And then we had priors on the betas and sigma squared. The priors for stream flow and the priors for all the other parameters are different. So let's see, beta 0J. Something like, I don't know if it was that big, 100 squared maybe.
I think it was.
Okay, so now let's talk about interpretation. Beta 0, when we have multiple categories, which we do with these seasonal covariates here, we have fall. These are indicator variables for fall, winter, and spring. So the missing season here is fall, winter, spring, summer. Yeah. So what we're going to have to interpret all of these with respect to those categories. So when all of these equals 0, we're talking about summer. So beta 0 and beta 1 are going to be interpreted as the slope and the intercept for stream flow during summer in the first year. Let's look at this graphically too. So, and we're going to have, I'll make this smaller. This is going to be stream flow. And this is our expected nitrogen count or value. So when all of our seasonal indicator variables equal 0, we're talking about summer. So let's start with that. And then we're going to have a beta 0 and a beta 1 for each of our sites. And we allowed those to change for each site. So we have different relationships between stream flow and nitrogen and expected nitrogen at each of our sites. we also have an overall mean for beta 0 and beta 1. That's described by mu beta 0 and mu beta 1. So this is kind of the overall, not kind of, this is the overall slope and intercept for all of our sites combined. I'm drawing single lines here, but there are posterior distributions associated with each of these lines. Let's look at a few of these. But before we do that, let's also consider the other seasons. We have beta 1. Let's see, beta 2 here describes the difference in the overall relationship between expected nitrogen count and stream flow in fall compared to summer. So I often call this the offset because it's kind of offsetting, and not kind of, it is offsetting the intercept for our model compared to summer, compared to our base group. And this is offsetting the intercept in winter compared to summer. And this is doing the same thing for spring. Yours is going to be continuous, so that's going to be a little different. So we'll come back to that. But we have graphs that look like this. For each season. And if we were putting this in a dissertation, we probably want to include each of those plots as results. Now let's go back to our code and look at some of these. One of the first things we can do is look at the posterior mean. Well, I'm going to show the trace plots first. This is really laggy. And I didn't fix that D norm. Yeah, it's interesting that log didn't do anything too. All right. So we have our trace plots. They look okay. That D norm missing from there may have done something to, so it's not quite off. But if we were to repeat this data sampling 100 times, about 95% of the credible intervals should cover that true value. And I think we're good there. If we look, I did look at the 95% credible intervals, and the true value is between those credible intervals. And we have, how many betas do we have? 2, 3, 4, 5, and 6. Okay. let's look at this graph that we just drew on the whiteboard. I'm going to look at stream flow between, what did we sample stream flow? What are the ranges of stream flow data? They're uniform between 0 and 10. So I'm just going to create a predictive vector that I'm going to use between 0 and 10 so we can plot out the relationship. So I'll say stream flow up pred equals the sequence between 0 and 10 by 0.1. And I'm going to use this to multiply by the beta values for stream flow so that we can see what that relationship looks like. All right, beta 0 dot mean. There were 7 different beta 0 posterior distributions, so there's going to be 7 different means. So this is the posterior mean. So there's our posterior means for our 1, 2, 3, 4, 5. Were there only 5 sites?
There were 7.
7. What happened to the rest of mine? Did I call
Harry,
it something else?
Don't you want to use, if we're doing beta 0, when you want to use the
I think that's the issue.
Yeah.
Yeah, beta.save only has 5 values.
Right, that's what it was. That's for year and season. Okay, our temporal component. All right, so this should have 7. I just missed the 0 there. These are going to be the points that I just drew on the whiteboard on the intercept. If we want to write mu, we can say beta 0 dot posterior mean plus beta 1 dot posterior mean times our values of stream flow. We're going to run into some issues in R calculating these because beta 1 dot PM has 7 values and streamflow dot pred is going to have about 100 values. So we can do these one at a time. Or we could do some fancier matrix multiplication, but I'm going to skip that for now. All right, so for our first site, this will give us our a line for mu.
Hey Perry, won't we have to make a posterior mean for beta 1 for that function to work?
That's what I didn't do. Thank you. I said, oh, I'm going to come back and do that, and then I never did. Okay, beta 1.save. There we go. That's pretty good that you could tell that with just looking at the graph. There we go. All right, so there is, we have stream flow shown on the x-axis, and then the posterior mean for beta 0 and beta 1 for the first site. Now I'm just going to go ahead and plot the rest of the sites on here so we can see what they are for the 7 different sites. And then we'll talk about looking at the different seasons. And change the Y limits a bit. There we go. Okay, so here's our relationship between the expected nitrogen count and stream flow, our predictor relationship. But this is only the mean. Remember, we have a posterior distribution for all of these values. The betas we used were the posterior mean from beta 0 and beta 1. Instead of using the mean, well, let's also use the mean, but I'm going to go ahead and plot some of the other betas for the intercept and slope to try and quantify or visualize the uncertainty associated with the beta values. So let me switch over to my code again. Here's what I did in the background to plot those other 6 points besides just the first one. I just put it in a for loop, and then I used the lines command, and I changed which beta I was using, which mean I was using. So now let's look at the very first site and put some of the uncertainty with the betas into that site. So I want to make a line, and instead of using the mean as I did here, I'm just going to take the second. Actually, I'll take the first iteration that we use. I'll take the second one because the first one was just our starting values. So I'm going to take the second iteration for both of these instead of taking the mean and plot that. So if I do beta 0.save for the second MCMC iteration, but the first site, and then I will add on the same iteration and the same site, just from beta 1, and then I'll multiply that by stream flow. And I'm going to I'll leave the color black for now. All right, so that gives me my Y values, but I also need my X values. All right. Any questions about that? Instead of using the posterior mean of the betas, all I'm doing is using that second MCMC iteration. And you can see where I'm going with this, right? If I, after do this, I do a third MCMC iteration, the fourth MCMC iteration, I would be plotting all these different lines that are slightly different based on what the values of beta 0 and beta 1 were for that MCMC iteration. So let's take a look at this. That's quite a bit different than the mean. So the line I just plotted was this one, and the mean for the first site was this black one. Now I'm going to put this in a for loop and do a bunch more MCMC iterations for the same site, and I'll plot it, and you can watch the plot come through. Actually, I'll show you my coding too. Lagging. I think when we take a break here, once we get done with interpretation, what I wanted to start talking about today was model checking. We'll take a break in 13 minutes. I'm going to restart my computer. We'll log back in because this is giving me some issues. It's really bad now. All right, I'm all locked up. Let's take a break now. We'll come back to it. So let's meet back here in 5 minutes. I got to restart my system, and then I'll start up. We'll have to log out of Zoom and then log back in. All right, talk to you then.